Thank you. My name is Tinashe, and I'll be presenting my work on hydrogen embrittlement of wire arc additively manufactured aluminum alloy 2319. So we'll look at the tensile properties and the fracture analysis. An overview of the presentation. So I'll just give a background and then follow up looking at additive manufacturing, followed by the experimental methods, the results, and then some conclusions. So the background. So with hydrogen in the UK, the Department of Energy is projecting that there will be growth in terms of hydrogen energy usage. So hydrogen will be used mainly in the transport and the energy sector as one of the alternatives for the renewable sources to for the 2040 net zero goals by the UK government. So how does this relate to additive manufacturing? So in terms of the future as well, additive manufacturing, there will be growth in additive manufacturing. This is because of its more sustainable manufacturing method. Some of the reasons are reduced buy-to-fly ratio, which proves it as a sustainable method compared to traditional manufacturing methods. So in terms of applications for the hydrogen environment, so we have pipeline valves manufactured by additive manufacturing. It can also be used to clad these valves. This is to protect them from hydrogen embrittlement or corrosion. Also uses in some hydrogen storage tanks, and there's research going on for additive manufacturing being used for proton exchange membranes. So hydrogen embrittlement, this has been explained. This was explained yesterday as well in the special lecture, and then today it has been explained. So according to the ASME standard, it is the loss of ductility in a material due to the presence of hydrogen. So some of the mechanisms, we've had some of this, and then these are the other three main ones. The induced phase transformation, mainly found in titanium. And then we have the induced decohesion mechanism, and they help. And then the synergistic effects of the latter two. For the experimental methods, so for those who are not familiar with additive manufacturing or wire arc additive manufacturing, it is a direct energy deposition process which is used to manufacture a component layer by layer using, if you're familiar with welding, examples are gas metal arc welding. So the process parameters that we use to manufacture the bulk materials are these ones, and the materials I've said is the aluminum alloy 2319, which is an aluminum copper alloy. So to introduce hydrogen into these specimens, electrochemical charging was used. So in terms of the variables, everything else was kept constant except the charging current density. This allowed the systematic evaluation of hydrogen embrittlement in this material. And then mechanical testing, which is tensile testing in this case, was done soon after the hydrogen charging using that 0.1 millimeter per minute strain rate. So for the microstructure of the additively manufactured aluminum, it's a complex microstructure because of the different thermal cycles imposed by each layer as you are manufacturing your bulk material. So these are three passes shown here. You have fusion line, and then for aluminum alloys, porosity is common in aluminum alloys. A close-up magnification of this shows so it's a magnification of between pass 1 and pass 2. We have these different microstructures. So there's aqueous grains, the fine grains, and the columnar grains. This result from the different thermal cycles. So tensile test results. As you can see from these results, we can see that there's a reduction in elongation as the charging current density increases. So to further illustrate this, we have the hydrogen embrittlement index, which is used to characterize hydrogen embrittlement. So for the results which I've shown in the previous slide, we see that there are minor changes in the UTS and the yield. However, there's significant changes in elongation or the ductility of this aluminum alloy. Looking at the fractography results of the aluminum alloy, as I've said, these are the common defects found in the additively manufactured aluminum porosity. This is due to a difference in hydrogen solubility in the liquid and the molten aluminum, which results in hydrogen being trapped. And then so these bubbles, or the small bubbles as you see highlighted in white arrows, form because of their gas porosities. So we see a ductile fracture, and we see some inclusions, some copper inclusions. As I've said, it's an aluminum 2000 series alloy. So some copper inclusions in the dimples for the fracture for the uncharged specimen. Now, looking at the comparison between the uncharged and the charged specimen. So with the specimen charged at 2 milliamps per square centimeter, we still see some micro void coalescence highlighted in orange there. And the fracture is a bit different to the uncharged specimens. And then looking at the other specimens charged at higher current density, we see that transition from the ductile fracture to a brittle fracture, which is explained in Professor Jovic's papers. So it's highlighted here. You can see that transition from ductile to brittle, and help and enhanced equation can use to explain this mechanism. So another fascinating thing that we observed in the results was some corrosion products on the surface of the specimen, closer to the surface. So an EDS analysis of this revealed chlorine, which is known as a pitting, which is known as a contributor to pitting corrosion in aluminum. So as I've said previously, for experimental method, we used sodium chloride as the charging electrolyte. So we also observed that there was some corrosion due to that electrolyte that we used. So in conclusions, while architekturally manufactured aluminum alloy is susceptible to hydrogen embrittlement, it also seen increasing the charging current density reduces the ductility of this material. Also, the minimal changes in the yield and the UTS of this material, and then help and enhanced decohesion were identified. And lastly, the pitting corrosion, which I've mentioned. I'd like to thank sponsors that have sponsored me for this trip, and very well. Thank you for the further questions.